Okay. So now see the thing is, there are two kind of antennas, right? So high gain antennas. Okay, these are all high gain antennas. Okay? So high
Mm-hmm.
gain, how we achieve, for example, if you are having single patch antenna, like this, okay,
Mm-hmm.
single patch antenna can give a gain of about 5 to 6 dB. Okay, 5 to 6 dBi gain. Okay.
Mm-hmm.
Okay, then, but if you want to have a long distance communication, so 5 to 6 dBi gain will have a radiation pattern something like this. Okay, so something like this. Okay, something like this. Okay, so but we need see what is radiation pattern? Radiation pattern is a power distribution. So the how the power is getting distributed, how the antenna is radiating, and how the power is getting distributed. That is what is the radiation pattern basically. Okay, so
Okay.
it is like a, then now if you want gain means what? Gain is actually a directivity, right? So how we are focusing the energy to the particular direction. So which means high gain means high sharpness towards the particular direction. So which means we are focusing all the energy towards a particular direction. Okay, so that
Mm-hmm.
what happens is, see here what we are doing, we are distributing the power in many directions. Therefore, the coverage range will be very limited. Correct. So
Mm-hmm.
coverage range will be very limited. But if you are focusing the same energy, okay, for example, some X power is there, it is distributed among this whole direction. Okay, but now
Mm-hmm.
what we are going to do, the same X amount of power, we are focusing in particular direction with the high gain. That is called as, so which means gain will be higher. Okay. So gain will be higher, beam width. So gain, so there are three parameters are there. Gain is inversely proportional to beam width, or beam width, you can say inversely proportional to gain. Okay. So whenever gain increases, beam width get narrow down. Okay. It is a similar analogy. You can see that torchlight is there. Torchlight. Okay. You might have some torchlight, some LED, or this kind of torchlight you might have seen, right? Correct.
Yes, yes.
So when
Mm-hmm.
you the olden days, the when you remove this, this is actually a parabolic reflector lens. You will have a
Mm-hmm.
lens over here, right? So
Mm-hmm.
when you remove this, it will be light range will be like this. So it will be spread across all the area, but the coverage range will be very less. When you connect this one, no, the coverage range will become increases, right? The
Mm-hmm.
same fundamental applies here also. Okay,
Mm-hmm.
same
Okay.
fundamental applies here also. So now, so when you want to move on to high gain antennas, okay, high gain antennas, then what are all
Mm-hmm.
the options are there? One is, parabolic reflector, which is, traditional way, more than I think 70 years, 80 years, they are using this parabolic reflector basically. Okay. So more than
Mm-hmm.
80 years are using this parabolic reflector antenna. So what it does is, see, you have feed horn will be there. Okay. It can be a feed horn or dipole, anything is fine. So what happens is this feed horn will illuminate the wave something like this. Okay. So what
Mm-hmm.
it does, it will correct the phase. So for example, you assume that, say, we always assume, right? So any antenna will radiate the energy in the spherical wave fashion. Correct.
Mm-hmm.
That's what you might have studied in any of the your subject. So spherical wave nature. So now what is happening? So this wave is reaching first, actually,
Mm-hmm.
in layman language. This is reaching. Means this particular component is this particular the energy is reaching late. Okay. So now what I'm going to do? I'm going to put a reflector over here. Okay, kind of a
Mm-hmm.
reflector. Okay, reflector. What it does? It's a metal, right? So what it
Mm-hmm.
does? It will just reflect. That's it. Okay.
Mm-hmm.
So here what is happening? So here what is happening? See, you can see here. This wave just impinge on this reflector. What happens? So it is, see, the exactly the phase is getting compensated, which means so this will reach here. So you see see the all will reflect at a time. How? Because this has to travel this much distance, but it will travel so till this part of the signal comes over here, so that for example, this spherical wave is coming, so you are having a reflector like this. Okay, so it has to
Mm-hmm.
travel this much distance, but it has this particular thing need to travel only the same distance, right? So for
Mm-hmm.
example, what happens is ultimately what we are doing, just correcting the phase, that's it. Correcting the phase, then a reflector wave will be like this. Reflector wave
Mm-hmm.
will be something, like, we can say planar waves. Okay. So planar
Okay.
waves. So, so by doing this, what we are achieving, for example, if you are having horn antenna like this, okay, so horn
Mm-hmm.
antenna, dipole antenna like that. So if you are having spherical waves, right, spherical waves, I am just telling in layman language. So for example, you are having, when you are when you are going, so the planar waves achieved in far field distance. We used to say that, right, more than 2D square lambda. If you keep, then you will, approximately receive the planar waves basically. So
Mm-hmm.
why we require planar waves? Because the problem is, see, for example, you are having one antenna like this, okay, that can receive this rays. So if you are having spherical waves like this, then what happens is, again you are achieving, you are getting the phase means phase deviation, right? That's why you may get it. That's why we always keep antennas far away from the far field distance. Okay.
Mm-hmm.
So then, okay, coming back to this. So that's why, so if you want to achieve planar waves very near to the, see, parabolic reflector achieve, used for two purposes. One is achieving the planar waves in near field terms, or we can say near field, far field the terms. Okay, in a shorter distance, if achieving parabolic planar waves. The other one is that, just see, if you are achieving the planar waves, so what happens is, see, your gain is getting, see, if you are correcting the phase, indirectly what you are doing, you are focusing the beam in the particular direction. Okay, so high
Mm-hmm.
gain is being achieved. Okay, so
Okay.
it is like a similar concept. For example, you are having one light. Okay, you just focus the mirror, you just keep a mirror in such a way that the light may be very 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 light. For example, it can be a LED light, but if you focus the mirror in towards some direction, it will be it will be focusing longer distance. Because how, what is doing, what it does is, it will correct the phase.
Mm-hmm.
So this is the parabolic reflector does. Okay, so the in complement of that, the phase array came into picture. So phase
Mm-hmm.
array, what we do, we see, we arrange patch elements in in this fashion. So we
Mm-hmm.
arrange it, array elements in this fashion. Okay, but each array will be fed like this. Okay, so there's something like that. Okay, so then
Mm-hmm.
it will be, it will be fed like this. So it's a corporate feed, series feed. So many feeds are there. Okay, so
Mm-hmm.
likewise, we will, we actually we feed like this. So we always feed like that. So what happens is, see here, see, this is spatially fed. Parabolic reflector is spatially fed. Okay, spatially fed means, so there is no connection between this horn antenna and this one. You might have seen in your home itself that there is a dish antenna, is that right? So that
Mm-hmm.
horn antenna will be there, and then reflector will be there. It is spatially fed one. Okay, here we are,
Mm-hmm.
what we are doing, we are feeding, in person. Means we are feeding each and every element with the, it's a conductor mode. We can say it's a radiator mode. We can say. So
Mm-hmm.
now, so this will enhance the gain. So what it does is, see, each patch antenna, for example, like this radiation pattern like this. This will have a radiation pattern like this. You might have,
Mm-hmm.
you might have studied array factor, right? So array factor, what it does. So see what array factor says. So if you want to, if you want to, means array factor, what it does. See, you will have a element pattern. Your
Mm-hmm.
element pattern. There will be a factor called array factor, because depends upon the, this factor depends upon the number of elements and the spacing between them, and how it is fed. So based on that, we can calculate the array factor. If you multiply element pattern with the array factor, so array factor, why we go, because we need not multiply each and every element radiation pattern together. So we will simply multiply with array factor. We'll get the array radiation pattern basically. Okay, so
Mm-hmm.
so the here what is happening is, see, constructive effect. Okay, constructive destructive effect will happen. So what happens is, see, it is a kind of a, if you have progressive phase shift, what happens is, see, you will, it will just um, all put together. See, this all energy getting collimated towards the particular direction. So that is like a high gain array. So means this all put together. We can say the effect. For example, LED light. Okay, if you have LED light, one single light separately, then your vicinity will be in this all direction, but shorter range. But if you arrange the LED light in such a way that the focus will be very long distance, right? That is what you might have seen in the street light. So the same principle it works here also. Okay, same principle works here also. So now what we are doing is like what we are going to do. We are going to study a reflector array, a reflector plus array, reflector plus array. So here what we are doing from see this is the for a parabolic reflector configuration, right? See, in phased array, what we did, we had a array of elements fed individually, correct? So here what we are doing, we are taking this feed, okay, the spatially feed, okay, and this array alone, not the feed, okay, leave alone this feed, and then we are array alone we are taking. So for example, what we are doing, we are going to arrange the array elements something like this, okay, something like this. Okay. So now what we are doing, we are taking this spatially, see from parabolic reflector, what we are taking, we are taking only the spatially feed mechanism. Then from the array, what we are doing, we are only taking the array of elements, not the feed network. Okay. Okay. So that is what is called as reflect array. Okay. Okay. So here what we are doing, so you see again, it is going to be a spherical wave, correct? So what we are going to do, we are going to calculate the phase shift that is to be introduced in order to compensate this. See, phase shift, phase shift, or time delay, or we can say um, wavelengths traversed. So all are interrelated parameters. Okay, for example, you have a sine waves, right? You have a sine wave. So if your wave traveling, for example, a quarter sine wave, which means so lambda by 4, which corresponds to 90-degree phase shift that you are introducing. Okay, and if you are traversing to one half wavelength, then 180-degree. Similarly, 360-degree here. So which means whenever you are traveling distance in terms of lambda, okay, then you are certainly experiencing or means assimilating the phase shift that is happening. Okay, so what happens is, so when a wave travels, okay, so the spherical waves, so for example, what we have to do, we have to compensate as we did in the parabolic reflector. Okay, so here what we use, so we have to compensate the phase with the planar array. Okay, that is the key here, the planar array. Okay, so here what we do, we introduce the phase in the each of the element. Okay, here also we'll have a, for example, like a parabolic reflector. So from we have a parabolic equation is we have. Okay, so I think x sine theta cos phi and sine theta sine phi, like that will be there. Okay, so what it does is spherical to rectangular coordinate systems. So spherical to, this is spherical, right? Spherical to rectangular coordinate system. There will be some equation will be there. I will share with you that, no problem. Okay. So if you read any book of reflector ray, in the first chapter or second chapter, they will discuss this, how to compensate the phase. Okay. So what it does is they have, if we have, for example, the parabolic reflector, this to be compensated at any point of time. Okay. Means, this to be compensated at each element, so that you will get the planar waves coming out of this. Okay. This is how it works. So now let me tell you how to design this reflector. Okay. So how to design this reflector. Okay. So we have two requirements. One is, you have to, you are going to fed, specially, and you have to compensate each and every location. So now we have this has you might have seen my video and my PhD Viva video, right? So you please go through that. I will, I have explained you. I have explained in a detailed manner this, how this works, how this space compensation is calculated, and everything is explained there. Okay, you can just go through my PhD Viva, um, so here what the two steps are there. I will tell you in brief. Okay. So what two steps are there? First step is element design. Okay. That's why they are asking increment report for element design. Okay. So here in this element design, what we do is we will estimate the, we'll estimate the element size, or we can say geometrical length of element size versus phase. Okay. Element size versus phase. So it will be something like this. Okay. So here, so from the parabolic curve, if you solve this equation and then using MATLAB code, we can able to find out each location what phase shift I have to introduce so that I can get the planar waves. Okay. Each location what phase shift I can introduce so that I can get the planar waves. Okay. So now here what we are having, phase versus location. Phase versus location. Okay, phase versus location. Here what we are having, phase versus element size. So what is common between these two? Phase. Okay. So then what you have to do, we ignore this and map this element size with this location. Map this element size with the location. So which means what? For example, here I'm, after into with the help of MATLAB code, I am finding that here I have to compensate 240 degree, for example. Okay, so 240 degree. Here I will go and check which element size is giving me 240 degree. For example, this part of the element. Okay, for example, this is something, we can say x1. X1 size of my element is giving 240 degree. So what I will do, I will place an element that is having x1 dimension. Similarly, here, for example, I have to compensate 120 degree. Okay, so now I will go and check which one is offering, which dimension is offering. So this is x2. Okay, so with this dimension, so then what I will do, I will map this. So I will place the element that is having dimension of x2. That's the, this is the array design basically. So element design is over. Then we are finding out the phase to be compensated. It has three steps. One is element design. Then, you are having, how to design the array. I mean, so find out the phase, and then then at last, array construction. So these are all the three steps you have. Okay. These are all the three steps you have for this, step. Okay. That's the only thing. Okay. So this is the overall view of this reflector array basically. Okay. So now element design. So see, element design is, it's kind of, design like of designing a patch antenna. Okay. For example, patch antenna is there. Okay, you have, patch antenna. Then you can see here. This is how you might have seen, right? By any patch antenna. Correct. Okay. So
Yes,
now,
yes.
here what we are doing, you are feeding individually. Correct. You are directly feeding at the patch. But we are here, what we do, the same patch only, what we do. So you have patch, okay. We spatially feed. That's the only thing difference. A unit cell element design is, so here we are feeding directly. Here, for example, if you want to design phased array, we will design like this, correct. Now here what we are doing, we are feeding spatially. That's the only difference that you find. Okay. That's the only difference you are finding now. Okay, that's the only difference. So you are spatially feeding this. That's the only difference. Okay, so here see, and before we move on, I will tell you one thing. Okay, so S11 no, S11 is a complex number, right? Reflection coefficient is a complex number, which will have a amplitude and phase. Okay, so how do you calculate the amplitude? If you take magnitude of to a plus jb, is that right? So what you will do? Your square root of a square plus b square. Similarly, for phase, what you do? Argument of tan b or something like that. Tan b by a, like that we will calculate, right? So S1 will have amplitude curve and the phase curve. Amplitude, so for example, something like this, you will get, right. This we call it as resonance, right? So resonance means, here, if you draw the, for example, impedance values, for example, Z parameter versus frequency, for example, frequency. So what you will get? So here, approximately, for example, if you take the real part, it will approximately crossing the 50 ohm. Okay, it will be approximately crossing the 50 ohm. If you look at the imaginary part, it will cross the 0 degree, see zero value. So the same, see the whatever frequency you are seeing is a resonance, right? So there you will see a real part, you will see 50 ohm, but imaginary means phase imaginary part you will see 0 there. Okay, 0 crossing there. Okay, 0 crossing is nothing but your resonance. Okay, so now if you want to translate this to phase, reflection phase versus reflection, phase versus frequency, for example. Okay, then here it will be 0 crossing. Okay, so 0 degree you will get it actually, basically 0 degree. Okay, 0 degree, why we are getting? Because we don't have any delay at that point. Because if, for example, delay, how it happen when you introduce L and C, when you are having R, it just dissipate the heat power. Okay, when you are having L and C, what you are doing indirectly, you are storing the energy and then releasing after some time. So that's why there will be a delay. Okay, when you are using memory device, there will be a delay. Means a memory component, for example, like L and C, there will be a delay. So if you are not using this, then you are not having any delay there. So therefore, zero delay, or we can say 0 degree phase shift that you are introducing. Okay, so that's why e power j omega, something like that we used to write, right? Any signal can be decoded as e power j omega sigma, or a sine theta, like that we used to write, right? So sine and e power actually can be translated as sine plus cos plus j sine theta, right? So why we are writing that? So exponential term, see, it has a magnitude part as well as the phase. Means we can say imaginary part, or real part and imaginary part. Imaginary part actually can be translated as phase, basically. Okay, phase or delay, whatever way you can take it. So this is the overall view of parabolic reflector, basically. So I think I hope you got something out of this. Okay. So
Okay.
yeah, you can share your screen, and then you can ask me any doubts that you have in CST. So CST, no, I have one link. I'll just share with you. There you will find
Okay.
entire this unit cell design, 2-3 videos basically. Okay, 2-3 videos. So right from the scratch, how do you design the we can say, how do you design the unit cell, and how to map the array and other stuff. So if you want to see, look at the mapped array, and then you can go through my PhD Viva. There you will get this information. Okay. So, but apart from that, if you want any preliminary information, you can ask me now.
No, sir, I'll go through the links and then I'll get back to you, sir.
Yeah.
That would be the case.
Yeah, you can just share me screen that problem statement, then or if you like to, or we can have a call later.
Yeah, okay, sir. Okay, no problem.
Yeah.
I'll look
Okay.
at the links and then I'll call you, sir. Okay.
Sorry.
I'll go through the links and then I'll call you back, sir. Like for doubts.
Yeah. Doubts. Okay. So now I go. I hope you got you got to know about these things, right? So
Yes.
any doubt in that? Actually, no doubt.
Okay, sir. Thank you, sir.
Maybe you might have got only 30% or 20%, but you can go through my PhD video, Viva video. There you will get to know more about reflectarray, and this CST videos, right? So that I will share with you now in the link, that page. That page I will share with you. So there
Okay.
you will get the uh, uh, you know so many what you can say, so many videos, because like you, so many people ask, right? So I I have shared that I have stored it as a video, so that I will just share with you that the link, basically. So where you will get a series of videos. I think through 4 or 5 videos will be there, that will tell you each and everything, like right from scratch. You please go through the description. Some particular video, each video will have a description. In that, what I have covered, that I have mentioned there. Phase unwrapping. So many things are there actually in estimating the reflection phase itself. Many things are there. First, we have to design the unit cell. Then we have to configure the unit cell approach and other things, and also then ultimately you will have what you will have is like you have to unwrap the face, and then you have to start writing the face, how to map these two, like that. So all the things are discussed over there. Okay.
Okay. Okay, sir. I'll go through it. Okay.
So thank you. Yeah.
Thank
Take
you,
care.
sir. Thank you.
Yeah.